Archimedes' principle. Archimedes' principle. When a body is fully or partially submerged in a fluid, a buoyant force Fb from surrounding fluid acts on the body. The force is directly upward and has a magnitude equal to the weight of mfg of the fluid. That's the weight of fluid that has been replaced by the body. The buoyant force involves two things. One is the fluid. This is the weight of the fluid. How much this mass is replaced by the body submerged in the fluid. Okay, so two things. One is the submerged body. One is the fluid. Okay, so there's the force equal to the mass, the weight of the fluid replaced by the body. The force is directed upward and has a magnitude equal to the weight mfg of the fluid that has been displaced by the body.
This demonstration will show how the buoyant force on a submerged object is related to the amount of water displaced by the object. This aluminum cylinder and pail hang from a scale, which shows the total weight to be 29 newtons. We'll lower the cylinder into this water container, which has an overflow spout. When the cylinder is submerged, the reading on the scale decreases to 20 newtons. All water displaced by the cylinder will flow into a beaker. If we pour the water that was displaced by the cylinder into the small bucket hanging from the scale, how will the reading change? The scale now reads the same as before the cylinder was lowered into the water. The buoyant force on the cylinder is equal to the weight of the water displaced.
Floating. When a body floats in a fluid, the magnitude Fb of the buoyant force on the body is equal to the weight mfg of the fluid that has been displaced by the body. This is very crucial Archimedes theory. So all these pressure, you have a result in Fb, buoyant force, upwards. Okay, we look at the magnitude of upward is the weight of the fluid replaced by the body. If the body is heavier than the flow, so this is gravitationally is larger than the buoyant cover, it goes down. If the body's gravitational force is smaller than the buoyant force, it will fall up.
Why do objects seem lighter when they are put underwater? We'll use this pair of kitchen scales in a frame to find out. The upper scale shows the weight of this aluminum cylinder. The lower scale shows the weight of this container of water. If we lower the cylinder into the water, how will those readings change? weight of the cylinder appears to have decreased by 2 pounds, while the weight of the water appears to have increased by the same amount. The water is pushing up on the aluminum, and the aluminum pushes down on the water by an equal amount.
We'll use these 3 blocks of wood to demonstrate how density affects the depth at which objects float. This block is cut from balsa wood, with a density of about 0.14 grams per cubic centimeter. When placed in water, it floats with only about 1/7 of its volume submerged. This is a block of pine, with a density of about 0.5 grams per cubic centimeter. It floats with about half of its volume submerged. This is a block of ironwood, with a density of about 0.9 grams per cubic centimeter. When placed in water, it floats with about 9/10 of its volume submerged.
This column contains 3 liquids with different densities. In order from the bottom, they are mercury, carbon tetrachloride, and water. We'll drop 3 objects made of different materials into the liquids to see where each object floats. Here is a piece of iron. It sinks through the first 2 layers and floats on the mercury. Here is a piece of bakelite. It sinks through the first column and comes to rest atop the carbon tetrachloride. This piece of wood floats atop the water. In this tank of water, we have a small plastic bottle full of air with an opening at the bottom. A weight at the bottom of the bottle makes the overall density of the bottle slightly less than that of the water. A syringe is connected to the side of the water column. As the syringe is compressed, the increased pressure compresses the air inside the bottle and increases its overall density. When the density of the bottle is greater than the density of the water, the bottle sinks to the bottom of the tank. Reducing the air pressure in the tank expands the air inside the bottle and returns it to the surface. If the pressure is continually adjusted, the bottle can be kept in the center of the water column.
Sample. The tip of the iceberg in popular speech has come to mean a small visible fraction of something that is mostly hidden. For a real iceberg, what is its fraction? We see the whole weight of iceberg is V iceberg, rho ice, so this is the mass, G is weight. The buoyant force is equal to the weight of the water, which was replaced by the iceberg, is called V under. Okay, this is the water's density. They should be the same because balance, when they balance, the force downward is equal to force upward. In this case, so with the rho I V I G equal to rho W V under G. And the percentage is VI minus V under divided by VI equal to 1 over V under over VI. And from here, V divided by VI equal to G cancel equal to rho I over rho water. We put this number inside. Okay, this is the density of ice. This is the density of water. Okay, we get about 10%. So when we see the iceberg with 10% above the water, 90% is under the water. In the figure, a block of density rho equals 800 kilogram per cubic meter flows face down in a float of density rho F equals 1200 kilogram per cubic meter. The block has height h 6.0 centimeter. Question A. By what depth h is the block submerged? Now we need a balance. What a balance? The balance is the Boyle force equal to the gravitational force because it's at rest. Okay, acceleration is 0. And we write that the force, the Boyle force equal to gravitational force. Well, this one equal to the weight of a liquid, which is occupied by the stuff. So it is a V5 floating, is merged part in the float. Okay, and this is the gravtation of the block. So the total V. These V are different. This part of it. Okay, so in this case, I can find FV. Okay, there's V equal to area multiplied H. Okay, and the total V is area plus big H. Okay, we know both of them. So in this case, we know that's H. Okay, H equal to H rho over rho final. We put a number inside. Okay, we use the centimeter as a unit. We get 4.0 centimeter. The key point is this one. Okay, that's physics. The Boyle force equal to gravitational force. Okay. Question B. If the block is held fully submerged and then released, what is the magnitude of its acceleration? Let's see the force. If it's submerged fully in the liquid, and this force is different from others. This is its weight, okay, mg. Okay, so we see the acceleration equal to Fp over Fg over m. What is Fb? Fb is total immersion, so this is equal to rho Vg because total immersion, and this is rho Vg, not different. This is the density of the block. This is the density of the float. Okay, and then we find acceleration, and we don't know the m, we don't know the v, but we know m. M equal to rho v. Okay, this is rho v. So the v cancel out. Okay, we got a. We have everything inside. We put a. So this is a 1200. This is 800. This is 9.8. This is rho is 800. Okay, and we found it. It's 4.9 meter per second per second.